It's a great pleasure to have Anthony Leverrier here. Anthony got his PhD from Paris in 2009, and he's currently at INRIA. I think he's worked extensively, on quantum coding. So he's worked on quantum expander codes, on fault tolerance with achieving fault tolerance with constant overhead. And, most recently, of course, he's been working on low density parity check codes, quantum LDPC codes. So, there are, of course, a lot of advances in the field in these last couple of years. There have been a number of breakthroughs. So really looking forward to hearing your talk about these. Anthony.
Thank you, Umesh. Thanks a lot for the invitation. Thanks everyone for coming. So today I want to talk about recent exciting developments in the field of quantum LDPC codes, and in particular the discovery of good quantum LDPC codes. It will be kind of the end of the talk. This recent breakthrough by Panteleev and Kalachev. And the goal of the talk is to introduce you to this field of quantum LDPC coding. Why is it important, and to present the recent developments in this field. But before I do that, let me start more gently with classical coding. Some reminder. So, it's been known since the 50s, since the work of Shannon, that if you want to send reliable information on a noisy classical channel, what you should do is to use redundancy. Basically, if you want to send k bits of information, what you should do is to somehow encode them into a larger message of length n, in such a way that even if you have some noise, even if you have some bit flips on your message, then you can correct for these bit flips. And the way to do that is to use this called a code. So a linear code will be just a linear subspace of the space of n bit strings. And the way we define it, so we have our n bits, x1, x2, up to xn. And the way we define a linear subspace is just by using parity check equations. So maybe you say x1 plus x2 plus x3, these 3 bits, they have to sum to 0 mod 2, x3 plus x4 plus x6, they have to sum to 0 mod 2, and you give a list of parity check equations like this. And then your code space is just, the space of all the words of the n-bit words x, such that hx equals 0, where h is this matrix that gives you these parity check equations. So h is called the parity check matrix. The code is nothing but the kernel of this matrix. So the code is a kernel. You have a code of length n that encodes k bits. So k is the dimension of the code. And the third important parameter for codes, for coding theory, is the distance of the code. Okay, so when you have a code like this, you don't want it to be arbitrary. You want to design it in such a way that every code word is far away from every other code word for the Hamming metric. Okay, you want that you're able to flip many bits, you have a large error, and you're still able to correct for it. Okay, so the distance of the code is just the minimum distance between two different code words, or because everything is linear here, is just the minimum Hamming weight of a non-zero code word x. Okay, and we have these 3 parameters, so the length n, the dimension k, and the distance d. Okay, so you denote the code like this, nkd. And so the goal of the field is usually to find codes such that the rate, so the ratio between k and n, the number of logical bits per physical bits, is as large as possible, and you want good correction capabilities. You want to be able to correct large errors. And so if you want to, what is an error? An error is just, again, a bit string, an n-bit string e, that will tell you which bits are flipped. Okay, and when you have an error, of course, you cannot observe the error directly. What you observe is x plus e, so the code word that you send, code word plus e. And what you can compute is the syndrome of the error. So you can compute h applied to x plus e, and it gives you h times e, because h of x equals 0. Okay, so S, this thing is a syndrome. And the decoding problem is the the following. You're given a syndrome, you have an error, you're given a syndrome, and what you want to do is to recover the error E of minimum weight, such that H times E equal S. Okay, and in general, this is a hard problem. It's NP hard if you have an arbitrary code, linear code. So you will want to design codes for which this problem becomes easy somehow. And so there are two kind of regimes of interest. You have the kind of the theoretical computer science regime where you want to consider adversarial errors. And there, the only thing that counts is somehow the distance of the code, because if you have an error of weight strictly less than d/2, then in principle you can recover you can look at the closest code word, and this will give you, the correct solution. And the other regime that is more relevant in practice is that of random errors. Okay, so maybe the distance is not so good, but the errors that will take advantage of this small distance, they are very unlikely, and random errors you can correct efficiently. So this is also interesting. And so one class of classical codes that has been very fashionable. So it's LDPC codes. So these codes were invented a long time ago by Gallagher in his PhD, like in '63, and then they were forgotten for 30 years because at that time, so Gallagher he invented these codes. He explained how to decode them, but at that time we didn't have the computational power to really use them in practice. So people completely forgot about those. And then they were rediscovered in the 90s. And so these classical LDPC codes, what are they? They are exactly what I've said, so linear codes, but with the special property that the graph here, which is called the Tanner graph, so that with the bits on one side and the parity checks on the other side, this graph should be sparse. Okay, so the degree of this graph should be constant. And when you have that, you have what you call LDPC code. So LDPC stands for low density parity check matrix. Okay, so you have a parity check matrix H, which is low density, which is sparse. So the number of ones per row and per column is a constant independent of n. So what is nice with these codes is that if you take just a random H, which is a random sparse matrix H, then with high probability you will get what is called a good code, meaning that K and D both scale linearly with n. Okay, so just do that, you get a good code. In the quantum case, it's not at all like this. We don't know how to get good codes like this. So good codes are easy to get, but what is more important is to get efficient decoding algorithms. And if you have an LDPC code, then you have this sparse graph, and then there's a way to exploit this sparsity to design good decoders. So you can design good decoders in theory that will work well against adversarial errors. This was the celebrated work of Sipser and Spielmann in '96, expander codes. And they also work well in practice. In practice, you have decoders called belief propagation that work tremendously well. And these codes, they are very successful. They are applied everywhere. They are used in Wi-Fi, in 5G. Okay, so in the classical case, we understand very well classical LDPC codes. And okay, so it's easy to find good codes like this, and we can design efficient decoding algorithms with proven properties and that perform well in practice. Okay, so now let's move to really what we care about today is quantum codes. Okay, so what's the difference between a classical and a quantum code? It's not that big. So in classical coding, you have basically one type of errors. The only errors that can occur are bit flips. Okay, bit is flips, 0 goes to 1, 1 goes to 0. In the quantum case, you have essentially two types of errors. You have bit flips again, and you have new errors, which are phase flips. Okay, and basically, because of linearity of quantum mechanics, you can show that if you can correct for bit flips and phase flips, then you can correct everything. Okay, so in essence, we only care about these two types of errors. And so we have two types of errors. So what is the solution? We need two classical codes. One will, take care of bit flips, and the other one will take care of phase flips. So, in kind of very roughly, a quantum code is nothing but two classical codes. But these two classical codes, they cannot be arbitrary. They need to satisfy some properties. And the properties that they need to satisfy is the following. So now the parity checks that we had before, they are a bit, somehow upgraded. They're not just, parity checks. They are really operators. So we'll have two types of operators. We'll have X-type parity checks and Z-type parity checks. So this one will, this will be poly operators that apply poly X operators on each qubits, and this one will be products of Z poly operators. And what you want to define a quantum code is you want that all these checks, they should commute pairwise, because somehow the quantum code will be the common eigen subspace with eigenvalue 1 of all these checks. So really what you need is that these checks, they commute pairwise. So this means that if you look at their overlap, so if you look at the support of this check, the support of this check is just these 4 blue qubits. So the qubits are in the middle, the checks, the X checks are on the left, the Z checks are on the right. So if you look at the support of this one, you have these 4 qubits. If you look at the support of this Z check, you have these 4 qubits. And if you want these 2 checks to commute, it means that their support should overlap on an even number of positions. So here it's fine, they overlap here and here. And in this case, for this code is called the STIN code. Okay, it encodes 7 qubits. You have 1 logical qubit, so you have a subspace of encoding 1 logical qubit. You have distance 3. But okay, so you need these checks to commute pairwise. So what does it mean? So it means, so if you have, so you want to define these 2 classical codes for each type of errors. So Cx will be the kernel of some matrix, Hx, Cz will be the kernel of some matrix, Hz, and this commutation condition can be restated as follows. It's just Hx times Hz transpose should be 0. Or said otherwise, equivalently, you can say that in this code, in Cx, you should have the dual of Cz. So what is the dual of Cz? Is just the code generated, product of Z checks gives you a word of DZ perp, and all these words, they should belong to Cx. Yes, we have these 3 equivalent conditions, and this is really the novelty in the quantum case. Okay, you cannot take arbitrary codes, you need this commutation condition. And then, okay, so you can define things as before. So the length of the code is just the number of physical qubits, and this will define, the code will define a subspace of dimension 2 to the k that encodes k logical qubits. So you have an upper bound, lower bound on k, which is just n, the number of physical qubits, minus the number of different checks. And kind of the novelty is the distance. The distance of the code. Now you have 2 classical codes. You have 2 distances. You want to be able to correct for x errors and z errors. So you have dx and dz. And dx is not exactly the distance of Cx, because in Cx, in this code, you have all the z checks that belong to Cx. All the z checks, they belong to Cx. But the z checks, they stabilize the code words. So they don't make an error. So they don't count in some sense. So really the distance, the x distance, is the minimum weight of a poly error or word that belongs to Cx, but that is not a sum of checks, of z checks. And similarly, dz, the second distance, is the minimum weight of a word that belongs to Cz, and it is not a sum of x checks. Okay. And then we have the same kind of notation as in the classical case, but with these double brackets. You have an nkd code that encodes, you have n physical qubits, k logical qubits, which are protected, and distance d. And just as in the classical case, you can define LDPC codes, and these will be codes for which Hx and Hz, these 2 parity check matrices, are sparse. But in that case, one very important observation is that Cx and Cz, these 2 classical codes, they are not good. They are not good because Cx, as I said already, it contains all the Z-type checks, which have constant weight, if you are LDPC. So Cx contains many words of constant weight. So this is not a good code. The distance is, the distance of Cx is constant. But the distance dx, you hope that it will be much larger than constant. Okay, so why should we care about quantum coding? Well, the main reason, and probably the reason we are all here today, is that the reason that the field of quantum computation exists is because of the threshold theorem. Okay, it tells you that if you want to perform some logical circuit on some qubits with m qubits, t gates, and if you don't have access to an ideal setting where everything is perfect, but on the contrary, everything is kind of noisy, and you have a physical error rate per gate, which is p, then you can still simulate the behavior of your perfect circuit if you use a fault-tolerant circuit which is slightly larger than the ideal circuit that you want to simulate. And this is possible provided that the error rate is below some threshold, okay, say 1%. But the cost for doing this is that the number of bits of qubits that you need is not m anymore, it's m times some polylogarithmic factor, m and t, the number of gates. So this is all very well, and the strategy to prove this theorem is to use code concatenation. So the idea is that, okay, you want to perform some computation with qubits, so the error probability is p. So what you do, every qubit, you will encode it with this kind of code, with the STIN code. So every qubit is encoded into 7 physical qubits. So every qubit is encoded in 7 physical qubits. When you do that, because the STIN code has distance 3, you can correct one error. So the effective, physical rate goes from p to roughly p squared. Okay, and if p squared is still too large, what you can do, you can do it again. So every one of your 7 new qubits that you had before, you encode them once again with the same STIN code, and now you have 49 qubits per logical qubit. And when you do that, the error rate drops to p to the 4th. And if you do L levels like this, and the error rate drops to p to the 2 to the L. And if you want to achieve some target, noise level, which is roughly, if you have t gates and m qubits, it's enough to have like an effective error rate that is below 1/mt. Then if you want to reach this level, you can just use log 1/epsilon levels. And then the number of qubits that you need to do that scales like m times polylog 1/epsilon. So this is how you get a polylogarithmic overhead for this threshold theorem. Okay, so this is a good start. But when I started my PhD like 15 years ago, I went to my first conference. It was QIPC in Barcelona. At that time, I was working on something completely different. I was working on classical quantum cryptography with quantum cryptography, QKD. I wasn't working on quantum coding. But there I saw the talk of David Poulin, and it really stuck with me. And David was saying, this code concatenation that we use for the threshold theorem is, from a coding point of view, is terribly suboptimal. The rate of this classical code that you use is terrible. It's really bad. So why not use better codes with constant rate, like quantum LDPC codes, to do fault-tolerant quantum computing? So I don't recall exactly all the details of this talk, of David's talks, but okay, I can reconstruct a little bit. So why do you need constant rate? If you have constant rate code instead of this concatenated scheme, then you encode k logical qubits into n physical qubits, and n and k, they are just relatively constant. Then you can hope to remove this polylogarithmic factor in the overhead. And so that's the easy part. Then the tricky part is that you need, the reason there is a code is because you want to correct errors during your computation. So you want to be able to measure the syndrome at each time step, and to correct the errors as they come. And you hope to correct errors at least faster, or not more slowly than they come. Okay, so you need like a good syndrome extraction procedure, and the syndrome extraction procedure, it will be faulty as well. It will be noisy. So if you want to be able to extract the syndrome in such a way that the syndrome is not too noisy, you want like the circuit to do this syndrome extraction that is constant depth. And if you want to do that, there's a scheme proposed by Peter Shor to do that, but it only works if the checks of the code, they have constant weight. So this is why we need a quantum LDPC code. If we want to apply this kind of ideas, we want a quantum LDPC code with constant rate. Okay, and then we can hope maybe to do quantum fault tolerance with constant overhead. Okay, so what are quantum LDPC codes? So I mentioned the definition before, but okay, let's try to look at an example. So I recall that what we want commuting X checks and Z checks of constant weight. Okay, constant weight is for LDPC, and we want a quantum code, so we want commuting X checks and Z checks. And if you try to figure out a code that will do that, and you want to do that by hand, you will get into a lot of trouble because it's not easy to do that. Somehow these two constraints, they don't go well with each other. And one brilliant insight of Kitaev at the end of the 90s was to say, okay, there's one place in mathematics where these two things, they kind of occur naturally. And this is in topology. And since then, I mean, topology has been very useful for designing quantum codes. And so the idea of Kitaev was to say, okay, let's take a manifold, so for instance, a torus, and then you put a tiling on the torus. Okay, so you put a tiling on the torus, and what you will do, you will put the qubits on the edges of this tiling, and then the Z checks and the X checks, you will define them like this. So you will have two types of checks. You will have X checks, so this will be star operators. So for each vertex, you will define an X check, and this is just the operator that applies a poly X on each of the four edges incident to a vertex. So you use that everywhere in the torus, and you define the Z checks for each plaquette. So for each plaquette, you take the product of all the Z operators around the plaquette. Okay, and if you do that, you can observe that these two types of operators, they commute. So either their support don't overlap, then they commute trivially. But then when they overlap, so say that you take the X check corresponding to this vertex, then the support, they will overlap twice. So one for this edge and one for that edge. And so you can check that you have the commutational relation that you want. And so you get the quantum LDPC code, with checks of weight 4. And this code is not bad. So it encodes, n qubits, the number of edges in your tiling. So sorry, the number of physical qubits is n. The number of logical qubits is 2. That's not so good, but okay, you encode something. And the distance of the code is not too bad. It's square root n. Okay, and today this is somehow the leading approach to do fault-tolerant quantum computing. So not with the toric code, but with a surface code, so like a 2D version, like a planar version of the toric code. But besides application for fault tolerance, this kind of codes, they have played quite an interesting role, in physics. Because they kind of give you new phases of matter. For instance, the quantum LDPC code is nothing but the degenerate ground space of some commuting polylocal Hamiltonian. Okay, and so you have this Hamiltonian which is local, and then you can look at the ground space, and it will display new properties like topological entanglement and so on. But really, the point that is important for this talk is that this toric code or the surface code, which is the close cousin, this is a leading approach to many attempts to do fault-tolerant quantum computing. And okay, what I would like to advertise in this talk is okay. So I stole this from Scott's well-known quantum PCP manifesto, and I want to advertise the quantum LDPC manifesto. Okay, so the observation is that this code, the surface code, it has been invented 25 years ago, and in the last 25 years, people have devised fault-tolerant techniques. They have developed these techniques to use these codes, with these codes in mind, with surface codes, 3D codes, and other variants. But these codes are not so good, and this leads to massive overhead, okay, for fault tolerance. So if you want to run Shor's algorithm to factor non-trivial numbers, like break RSA or something, the number of physical qubits that you need per logical qubits is maybe 1,000, 10,000. So this has a huge cost. And somehow the approach I would like to advertise is to say, okay, maybe what we should do is to find good quantum LDPC codes first, and then try to use them into fault-tolerant, to do fault-tolerant quantum computing. Instead of using the bad codes that we had before. I mean, bad in the coding theory sense. So let's try to find good quantum LDPC codes first, and then exploit those. And probably along the way, we'll get also new interesting results, like new exotic phases of matter, unexpected consequences in complexity theory, and so on. Okay, so what do we want? We want good LDPC codes. So this is what I will talk about in the rest of the talk. We want efficient decoding, so we are not there yet. And we want also something that I completely omitted for now, is the ability, to perform logical gates with these codes. And for this question, I mean, much more work is needed. So I won't talk about that today. Okay, so can we get better quantum LDPC codes than the toric code? So yeah, in the past 20 years, people, one avenue that has been very fruitful to design new quantum codes is the topological approach. Okay, so the toric code construction is beautiful, and you can generalize it in a number of ways. So you can take any manifold that you want, not a torus, but anything that you want. You can work in any dimension that you want. You can work in Euclidean space. You can work in hyperbolic space. So you can generalize this approach to get a flurry of different quantum codes families. But somehow all these codes constructions, they suffer from very strong limitations. Particularly one result, important result from Bravi, Poulin, and Barbara from 2009 is that all these codes, if you look at their parameters, K, D, and N, K and D cannot be arbitrarily large. Okay, in particular, if you look at two-dimensional codes, topological codes, like the surface code or the toric code, you have the constraint that K times D squared should be order of N. Okay, so if you, and the toric code kind of, satisfies this. For the toric code, you have K equals constant and D square root N. Okay, and you can generalize these results to say that good codes, they will require a lot of long-range interactions. Okay, so the kind of the lesson, if you want to get better codes, is that you can keep sparsity, you can keep the idea that you want a sparse parity check matrix, but you should drop this this constraint of having geometric locality in D dimensions. So that's one lesson. And the other thing that I want to stress is that in the classical case, getting a good, just proving the existence of good LDPC codes is trivial. You just take a random parity check matrix and you can prove that it's good with high probability. In the quantum case, if you do something purely random construction, it won't work. And the reason is as follows: if you have two matrices to take, Hx and Hz. So if you take Hx to be random, then with high probability, just because of the classical case, the distance of the classical code corresponding to Hx will be large, will be linear in N with high probability. But you have this commutational relation that you want, and this commutational relation says that the support of the Z checks, they should be code words of Cx. And so it cannot be the case. So if this is true with a Hz which is sparse, then it's not possible that Hx has distance order of N. The distance of Hx of Cx should be order 1. So if you take a purely random construction, it won't work. So you need a little bit of structure. But it's very hard to take the right amount of structure. If you take a bit too much than what was done for the topological constructions, then you get too much structure somehow, and you get this, these upper bounds. So you cannot get good LDPC codes. So you really want to find the minimal amount of structure that you need to ensure commutativity, but at the same time to keep a good distance and a good rate. Okay, so this has been a very complicated problem for the past 20 years. Okay, so in the beginning of the talk, I want to explain to you how to do that. So how to get good quantum LDPC codes. So K and D both linear in N. So it's a story in 2 acts. So the first act is to boost, the dimension. And the second act would be to boost the distance, which is harder to do. Okay, so how to boost the dimension? So again, it was like a beautiful insight from Tillich and Zemmour in 2009. What they observed is that a torus, you can see it as a product of 2 cycles. Okay, the red cycle and the blue cycle. If you have the blue cycle going around the red cycle, then it will draw a torus. And then if you have a cycle like this, or if you look at the classical code with Steiner graphs, so the graphs that I had before correspond to a cycle, it's just a repetition code. Okay, so in some sense, in some well-defined sense, the toric code is nothing but the product of 2 classical repetition codes. Okay, so if you have 2 repetition codes, so a repetition code has length n, it encodes 1 bit. So you have 2 words, either everything is 0 or everything is 1. And the distance is n, because you have 2 words and they have maximal distance. You need to flip all the bits to go from the all 0 word to the all 1 word. So the parameters of the repetition codes are n1, n. So if you take the product of 2 repetition codes, you get the toric code. And then what Tillich and Zemmour asked is whether you could somehow generalize this to products of arbitrary classical codes, not just the repetition code, but you take 2 arbitrary codes and you would get a quantum code. And it turns out that you can do that, and this is exactly what they did back then. So if you take 2 arbitrary classical codes with parameters nkd and kd, then you get a quantum code of length roughly n squared that encodes roughly k squared qubits and that has distance d. If you had distance d squared, then this would be wonderful. You would get good LDPC codes. Because if you take 2 classical LDPC codes, you get a quantum LDPC code. But unfortunately, the distance, it's not squared. It's just basically the minimum of the 2 classical distances. But still, if you take the product of 2 good LDPC codes, you get a quantum LDPC code with constant rate, okay, and minimum distance square root n. So basically, you get a huge improvement compared to the toric code. You keep the same scaling for the distance, but the dimension, it goes from constant to linear in n. Okay, so that's very interesting. And this construction is a very special case of the homological product construction of Ravi and Hastings. So they managed to generalize this to, you can take products of quantum codes and you will get another quantum code. Okay, so this is already quite good. And it turns out that this is, it's even better than expected because thanks to a result of Daniel Gottesman, published in 2013. So Daniel had the colloquium about this last year. So what Daniel did in this paper is to show, how to use these almost good quantum LDPC codes to perform fault-tolerant quantum computing with constant overhead instead of polylog overhead. And in this recipe, you need 2 ingredients. So you need 2 things. You need reasonably good quantum LDPC codes. So you need concentrate quantum LDPC codes. So the dimension, the number of logical qubits should scale linearly with n. And you want the distance to be not too bad. Okay, but you don't need it to be linear in n. It's sufficient if the distance grows, polynomially with n, with any, exponent which is above 0. So this is kind of easy to do. The hypergraph code construction just gives you that. What is also needed in Daniel strategy is you need a very good decoder for this code that will, correct errors very well. And the very hard part to get is you need like a very efficient decoder. You need the decoder to work in constant depth. Because the idea, if you recall, the way you would do the computation is at each time step between your logical gates, you would measure the syndrome, then you feed the syndrome to a classical decoder, then the classical decoder tries to guess what is the most likely error, and then you correct for the error, and then you continue with your computation. But the point is that during the time where your classical decoding algorithm tries to compute the most likely error from the syndrome, during that time, the noise still accumulates. So if that time is too long, then the noise will accumulate too much and you won't be able to correct anything. So it's very crucial to have a very fast classical decoder for these codes. And what we did a few years ago is to show that if you take the hypergraph product code of two classical expander codes, and if you use a special decoding algorithm called small set flip, then you have these two ingredients, and then you can apply, Daniel recipe to get quantum fault tolerance with constant overhead. So in some sense, this gives already a positive answer to David Poulin's vision, which was, so, okay, let's use quantum LDPC code with constant rates to get constant overhead fault tolerant quantum computing. Okay, but in some sense, we are still not very happy. It's still a bit frustrating that these codes are not as good as one might hope. Okay, so the big question is, can we get even better quantum LDPC codes? Can we get the distance to be much larger than square root n? And if we can, maybe this will lead to much better thresholds, fewer assumptions on the noise model that you need to have these fault tolerant schemes to work, and so on. So, okay, so let's try to do that. So before I explain to you how we can beat this bound, let me explain why we were stuck for many years at this bound. So this hypergraph product construction that I mentioned, I didn't explain it in detail, but the way it works is as follows. So you take two classical codes, CA and CB, so you have n bits and n minus k parity checks, n bits, n minus k parity checks. And this hypergraph product construction, it takes these two classical codes and it turns them into quantum code. And the quantum code will look like this. So you have two sets of qubits, like this huge square n by n set of qubits. Here you have an n minus k times n minus k set of qubits. Then you have a bunch of x checks and a bunch of z checks. I won't explain in detail how it works, but the idea is that all the columns here in red, they are somehow copies of this classical code CA, and all the blue rows that you will have everywhere, they are copies of CB. So here you have your n bits if you want, and you have the n minus k parity checks. Okay, so the quantum code, this hypergraph product code, it consists of many copies of the classical codes that you started with. And what is not so good is that if you take a code word of the classical code of CA, so a bunch of bits that will satisfy all the equations, then this code word gives you a logical operator of the quantum code. If you just put the same code word in this column, if you put a code word of CB in this row, this will give you, logical operators. And because of that, the distance of the quantum code cannot exceed the length of the row here or of the column here. And if you optimize, the two distances should be equal. So you end up with a distance which scales like square root of the number of qubits. Okay, the distance is really the length of this row, and the number of physical qubits is the number of rows times the number of columns. Okay, so this is, and all the construction that we knew before, they were following this kind of pattern, and we were really stuck with this square root n bound for the distance. Okay, so how can we beat this? Because we can now. We didn't know that 2 years ago, but now we know. Okay, so before I tell you that, let me just quickly recap the history of quantum LDPC codes with large minimum distance. So I already mentioned topological codes. So in 1997, Kitaev, he devised this historic code that gives the distance square root n. Then a few years later, Friedman, Meyer, and Liu, they use much more complicated manifold instead of the torus, and that improves the distance a bit, but it's really a little bit, just by a factor log n to the 1/4. Okay, and then for 20 years, nothing happened. But somehow in the past few years, I mean, in classical coding theory and classical complexity theory, people started to explore new kind of objects, high-dimensional generalization of graphs, exponential graphs. And somehow this kind of new objects, they give rise to interesting quantum codes. And in 2020, I mean, there were 2 papers using these kind of ideas to improve a little bit on the bound, on the distance, but not by much. First square root n times log n, then square root n times log n to any constant. But still, we are stuck at this square root n, at this O tilde square root n bound. And then really the breakthrough occurred just 1 month later. So first in a brilliant paper by Hastings, R, and O'Donnell. So it was really the first paper that broke the square root n bound with this fiber bundle construction. So they managed to get the distance n to the 0.6. Then a few months later, there was like an explicit construction of these codes and a conjecture by Brockman and Eberhardt called these balanced product codes that could give potentially, good quantum LDPC codes. And again, in December of that year, in 2020, Panteleev and Kalchev, they managed they invented lifted product codes where the distance is almost linear. It's n divided by log n, which is really, really good. But at that time, the dimension was not so good. So k was just logarithmic in n instead of linear in n. So this was like 1 year ago, and then probably you've heard this, but a few months ago, November, so the same colleagues, Pavel Panteleev and Gleb Kalchev, they managed to finally achieve the Graal of quantum coding, so to prove the existence of asymptotically good quantum LDPC codes. And sort of unexpectedly, this construction, it also gave a construction for a different object that is interesting in classical complexity theory, which is, or classical coding theory, which is called a classical locally testable code. And on the same day that this paper appeared, there was another paper devising, this kind of locally testable codes. So there was a talk by Irit Dinur last year and the breakthrough, series of the Simon's Colloquium. So you can watch this talk if you want. And the reason I mentioned these 2 things is because, I mean, the first paper, the quantum LDPC paper, as a byproduct of the quantum LDPC construction, they gave also a solution, construction of locally testable codes. And it turns out that this kind of 2 objects, they are very connected. And now we have a few more examples. So an example that we'll talk about, construction by myself and Gilles Zemmour, we also give a construction for quantum LDPC codes that gives also classical locally testable code, exactly the same as in the Dinur et al. Paper. And so now the state of affairs is this. You have these 2 kind of objects, classical LTCs and the quantum LDPC codes. And it turns out that every time you have a quantum LDPC code, it gives also a classical locally testable code. So we have 2 constructions of quantum LDPC codes, or 2.5, and we have 3 constructions of classical LTCs, and 2.5 because there's been recently a paper by Lin and Xie where they give a construction of classical LTC and they give only a conditional construction of quantum LDPC code. It's conditioned on the on verifying a conjecture for that some objects exist. Okay, so how do we break? How do these papers achieve to break the square root n barrier? So here is kind of the intuition. So if you recall the hypergraph product code that we had before, so somehow just look at the top slice of the picture. It was what we had before. So we had like many classical codes, many copies of the classical code, the red copies and the blue copies. And somehow, if you have a word of the classical code in this copy, it gives you a logical operator of the quantum code. So the idea to break this square root n bound is to somehow add a 3rd dimension, and to picture what you would like to have is something like this. So you would like to have many copies of a classical code, but now the classical code, they correspond to a slice. So either a red slice or a blue slice. And the hope now is that, because these slice, they share a lot of, degrees of freedom, all these vertical coordinates. The hope is that, classical world of the red code will be something that, has weight, like linear in the size of the slice. And now, because the weight of the slice compared to the total size of the quantum code, which is this cube, is much larger than before. It's just, you have only delta slices like this. So you could hope to get a distance that scales like, the length of this, the height of this cube. So n divided by delta squared times delta. So you could hope to really improve the distance in this way. And this is exactly what happens for the quantum Taylor codes that I will explain in a minute or two. But so to do that, we need more structure than we had before. So before, with this hypergraph product code construction, you could take two arbitrary classical codes and they would always give you a quantum code. Now somehow you need some structure because you need the two codes, the blue code and the red code, to share all these vertical degrees of freedom if you want. So you cannot take arbitrary codes. So you need more structure. And all the papers I mentioned that beat the square root n bound, they all use different terminology, but somehow behind the curtain, it's always kind of the same topological, if you want, tool that you use. And it's probably this balanced product construction of Breukman and Eberhardt. So in some sense, you could say that all these examples, they are specific examples of this balanced product construction. Okay, so I won't explain these three codes because somehow they are a bit complicated. I will try to focus on this one, which hopefully is the simplest one to understand. So quantum Taylor codes. But before I do that, let me just quickly go through the classical case because Taylor codes have been invented for classical coding. So they were invented by Taylor in '81. And the idea behind these codes is to build a large code from a delta regular graph. So you have a graph of degree delta, and you have small codes of length delta. And the idea is to put the bits on the edges of the graph. Okay, so you put the bits on the edges of the graph, and you put the constraints on the vertices. And the way you put the constraints is by asking the local view here of this vertex. So the vertex, it views a number of bits, a number of edges. You will ask that the restriction of the code word to this, here 4 or 5 bits, this has to belong to some small code. Okay, so that's the idea behind Taylor codes. So first example of Taylor code is product codes, also known as tensor codes. So in that case, the graph that you take is just a complete bipartite graph. So you have n bits on one side, n bits on the other side, n vertices on one side, n vertices on the other side, and you have n squared edges, so n squared bits, and you have two types of local views. You have the local views from the A side, from the left side, and you have the local views from the B side. And the way it works is that somehow the A side, it gives you a partition of so here the square is supposed to represent all the edges. Okay, so the edges, they are somehow, labeled by A times B. So you start from any vertex A, and then you have B choices to define your edge. So the edge set is isomorphic to A times B. And the product code is just this, is just you ask that if you look at the restriction of the code word on every column, it should be a code word of CA, of some classical code CA. And if you look at the restriction on any row, it should be a code word of some classical code CB. So this is the product code construction. another construction that was, very important in the field of quantum LDPC coding is the expander code construction. Here, the idea is to take, the next best thing after the complete bipartite graph, you take an expander graph. So somehow it's, I won't explain what expander graphs are, but it's just like somehow a sparse graph that behaves somehow like the complete bipartite graph. And one way to define this graph is as follows. You can just, you take a group G, and your vertices, there will be 2 copies of the group G. And then you take a subset of G, subset A. And then, so the vertices, they are elements of the group. And then you put an edge between 2 vertices, G and AG, if you go from G to AG by multiplying G by A, an element of the set A. Okay, and so you do that everywhere. If you take the subset A to be of size delta, and your graph to be of size delta, then you can enforce, local constraints. You will ask that, each local view here is a code word of some small code, C0. And if you take a good small code, and if you have an expander graph, you get a good, expander code with, efficient decoding algorithms. But some of the important part here is that this, when you look at this, you have 2 types of views. You have the views from the left, the blue ones. You have the red views from the right. And these 2 types of views, they give you 2 partitions of the set of edges. Okay, so this is some of the set of edges, G times A. So you start from any point, any vertex in here, and you can, for any vertex, you have A possibilities to define an edge. So these 2 types of local views that define 2 partitions of your set of edges, of your set of bits. Okay, and so in the quantum code construction, for the quantum Taylor codes, what we want to do is to take, we need 2 classical codes, Cx and Cz. And what we will do is we will take these 2 codes to be both classical Taylor codes. But somehow to do that, we need 4 partitions of the qubits. And recall that we need this commutation constraint. This is the hard thing to get. And so to get the commutation constraint, you cannot take a graph like this, because if you take a graph and you enforce constraints, so say X checks on the left, on the blue things, Z checks on the right, on the red things, then X and Z, they will either not overlap or they will overlap once. But if they overlap once, they won't commute, they will anti-commute. So this won't give you a way to get to quantum code. So the idea to get to quantum code is to go and, to move to something a bit higher dimensional than a graph, and to move to a more general complex, where we will replace the edges. We won't put the qubits on the edges, but we will put the qubits on, squares. Okay, and so the tool to do that is really the left-right Cayley complex that was defined by Diner et al. So in the quantum code construction, what we need now, we need 4. So we need a group, as before, G. But now we take 4 copies of G. And then we need 2 subsets, A and B, okay, of G. So A and B are both of size delta. They are both of constant size. And now we have 2 types of edges. We have blue edges, so type A. So G will be connected to AG between these 2 sets of vertices. Here, some GB will be connected to A times GB. And we have red edges that correspond to the set B, where G is connected to GB. So it's important that, it's called left-right complex, because when you move with A, A acts on the left of the group element. And when you use a B-type edge, B acts on the right. Okay, and when you have this, so you have these edges, but what you have now in addition is you have many squares. So a square is just this thing that I represented here. So you have G, you can go to A times G, and then if you make a B, B step, you go to AGB. But you can go either way to AGB if you go first through GB and then to AGB. Okay, so this this thing has a lot of squares like this. The number of squares is the squares. They're labeled by G times A times B. You have group elements here, and then you have to choose an element of A and an element of B. Each local view, so for each vertex, at each vertex you see delta squared squares. So the local views, they are isomorphic to A times B, and you have 4 types of views. So before you had 2 types of views because in the graph case you have an edge that can belongs to it's incident to 2 vertices. Now you have a square and it's incident to 4 vertices. So you have 4 types of views. And what we want to do is, we want to define 2 types of constraints of checks, X checks and Z checks. So we'll have, red local views for these 2 types of vertices and blue local views for these 2 types of vertices. And if this is the set of all the squares. So we have 4 types of vertices of views, which are all of size A times B. And really the crucial point is that when you have 2 local views, so a blue and a red local view, they will always share either a column or a row, okay, or nothing. But say this one and this one, if you make them to overlap, they will share this kind of row or column. And this one and this one, they will share this row or column. So the way you can get, a quantum code. So now you have the checks. They can overlap on a large number of qubits. And the way to get a quantum code, the way to get commutation is by putting checks that correspond to tensor product codes, code words. With 2 types of codes, CA and CB, and the dual of CA and CB. Okay, so for instance, here you have X checks, here you have Z checks, and if you take the blue view that will overlap with this red view on this column, for the red check it will be a code word of CA. For the blue view it will be a code word of CA perp. So they will be orthogonal, so they will commute. So this is the way you enforce commutation with this kind of complex. Okay, so the quantum Taylor codes, they are this. So you get an explicit construction. You use a Diner et al. Left-right Cayley complex. In their paper, they give an explicit construction of how to get that. To get quantum Taylor codes, you can just pick the small codes C and CB to be random codes. And then you get a quantum LDPC code with constant rate, which is positive. And the main result is that if these things, so if these 2 codes, so these 2 codes, CA times CB perp and CA perp times CB perp dual, these 2 codes, they are the dual of product codes. So if these 2 codes, they are robust, and I will explain what this means, then you can show that the distance of the quantum Taylor code is linear in n, and the bound is essentially tight. And this is exactly what happens, what I described before. The logical operators, they will be in a single slice, as I showed before. So this robustness, it will hold with high probability for any epsilon which is positive. And as a corollary of this result, we obtain exactly the local testability of the locally testable code of Diner et al. So I don't know how much time I have left.
It's okay. You can take a few more minutes.
Okay, I have just to quickly explain the idea behind the proof of the distance of this code. So I mean, the proof strategy is kind of always the same. So you start with a logical operator, a logical word of small size, so below the minimum distance. And what you can do is you show that. So you have a word of CX, and then you show that if this word has weight which is too small, then you can decrease this weight by just adding a generator of the code. And then you can repeat this, and you will decrease the weight until you get to 0. And in this way, you prove that X, this code word of CX, was in fact a sum of generators. So it does not count for the minimum distance. So the minimum distance has to be larger than this. And the way you prove that, okay, so let's say that we look at the X type error. So it should satisfy, if it's in CX, it should satisfy all the blue constraints. And the blue constraint, they ask you that the constraint, the checks are the element of CA perp times CB perp. So if you satisfy the check, you commit with the check, means that the local view belongs to the dual of this tensor code. And the dual of a tensor code is an interesting code. It's just, so a tensor code would be every row and every line is an element of the code, of the small codes. The dual tensor code is a bit different. It's the local view is a sum of some columns and some rows, which are either in CA or in CB. And so X, any code word that you have, it's actually a code word of a classical tenor code defined on a delta squared regular expander graph, but with bad local codes, because the local codes that you use are really dual tensor codes. And these dual tensor codes, they have a poor distance. They have distance delta instead of delta squared. And the locally testable code of Dino et al. Is exactly the same. Instead that you take for the small codes, you take the tensor codes, CA times CB. And these ones have large distance. So in our case, X is a code word of a bad classical tenor code, but this is necessary because we know that the classical CX must contain the Z checks. So it cannot be a good code. So if you want to analyze what happens, you really need to exploit the structure of these dual tensor codes. And this was done in the paper by Pentelef and KHF. And they showed that for this dual tensor code, you have a very special property, which is, if you have an element, so the code word is just a sum of columns and rows. If you have a sum which has low weight, say lower than this, then you can always write it as a sum of very small number of rows and columns. Okay, in some sense, you cannot have too much cancellations between rows and columns if the final weight is small. So that's the crucial property that we need. And then the proof is not that complicated. So, so you have a word which is this, a word of this classical tenor code. So in each blue view, using expansion in the graph, you can show that the local degree is not too large. It's order of delta, and the size of the view is delta squared. So because of that, you can use robustness of the dual tensor code to say, okay, this view actually corresponds to a sum of a constant number of rows and columns in each of these local views. So in particular, for each of these local views, the columns and the rows, they don't perturb themselves. Okay? The rows won't perturb much the columns, and vice versa, because you have only like a constant number of rows and columns. So it means that in these local views, every row and column is very close to a code word of CA or CB. And then you can use expansion properties of the Cayley complex to show that all these non-zero code words, all these non-zero rows, they have to agglutinate somehow in the red local views, in the other type of local views. And so in this other type of local views, because of what we said before, all the rows and all the columns, they must be very close to code words of the small codes. And then you can use the robustness of tensor codes. This is something that is well known classical coding, to show that there has to exist at least one red local view where the local view is very close to a code word of CA times CB. And this is nothing but like a check, a generator. So you can flip this generator, and then this will decrease the weight of X, and you can repeat this until you get to 0. And so this proves that X is a sum of checks, of generators. And this proves the lower boundary distance. Okay, so that concludes what I wanted to say. So to summarize, so I mean, for 20 years, nothing much happened, in quantum LDPC code, in the coding theory. We were stuck at distance of order square root n. And then in the past 18 months, there has been tremendous progress. And now, thanks to this result by Patayev and Kayachev, we know that good quantum LDPC codes exist. And we have even a simplified construction of this. And now the big question is, okay, can we use that to do something interesting for fault-tolerant quantum computing? I mean, it has to be the case that these codes, they have to be good to do fault-tolerant quantum computing. So this opens like a flurry of new open questions. Okay, find better good LDPC codes with efficient decoder, small size. Something that I completely ignored in this talk is how to perform logical gates on these general LDPC codes. So there are papers that start to appear on these questions. And of course, something that I completely ignored is, okay, how do you implement these things? Okay, so this is a challenge for experimentalists. So you really need to implement these things. And so this means that you need qubits that can interact. And you need long-range interaction to make these codes possible. So that's a huge challenge, of course. Okay, and that concludes what I wanted to say. So thanks for your attention.
Great. Thanks very much for giving us such a great panorama of this field, and also of catching us up on the recent work. It was a fantastic talk, Anthony. Thanks a lot. So, so there are a lot of actually experts on this subject in the audience and also on the panel. So let's see. Are there any questions before we move on to the panel? Perhaps we can roll in questions also with the panel itself, since we are running a little bit low on time. So let's go ahead and if you can stop sharing your slides, Anthony, then we can get the panelists' videos pinned. So we have a really fantastic panel which has, let me introduce the panelists. So Barbara Terhal, who's at the Delft University of Technology. She's worked for a very long time on on quantum, on all aspects of quantum information, but the one thing that she her work has focused on particularly, which is important for this particular panel, is on both quantum error correction and fault tolerance. And so great to have you here, Barbara.
Thanks, Umesh.
Yeah, and there's also Daniel Gottesman, who again, he's a physicist by training, but he just moved to University of Maryland, where he has a professorship in the computer science department. So he really crosses between the two. And of course, he's worked on various aspects of quantum error correction, fault tolerance, including introducing the notion of stabilizer codes. And our third panelist is Matt Hastings at Microsoft, who's again, everybody on this panel has had this, extremely wide view. So Matt is, he's done, I guess, as much as anybody else to create this field of quantum Hamiltonian complexity, and of course he had a big role to play in this story that Anthony told us. So it would be great to hear each of your views about this whole subject. I guess there are many things to talk about, including things that Anthony said about how close, how far are we along this road with quantum LDPC codes in terms of parameters, in terms of efficient decoding. There's also issues about fault tolerance. How do you, when you're working with these large codes, how do you do your operations? Do you do them? Do you do single bit operations at a time, or can you actually parallelize them? There's also the complexity theory aspects of this. What are the implications of this work for NLTS conjecture, or for are they going to be, you know, what's, you know, or quantum LTC, and then there's of course physical implications. Anthony spoke about, well, you know, how Kitaev's code, you know, introduced a new phase of matter. So, are there physics implications of all these codes? So I'll just turn it over to each of you and see what you have to say. So, would you like to say something, Barbara?
Okay, I'll say something. Yeah, of course, I think it's fantastic, of course, that there's such a breakthrough and that we understand this a lot better now. And I think there probably will be further consolidation of these codes and these various constructions to understand it. I think for myself, I have always felt that maybe for practical purposes, which are not necessarily mathematically so interesting, it's threshold that counts a lot, right? At this stage of development. And as far, maybe Anthony can comment on this, or somebody else, that I think this is a bit open whether these codes are going to be very good in that respect. And then the other thing is, as Anthony said, the embedding. And so I'm sure they'll find some place in quantum computing, but where exactly and at what time, to me, that's still a bit open. Yeah, so that's one comment I'd like to make. I don't know if anybody can respond. I guess people can respond, or other people on this whole panel, can they respond, or just it's just
absolutely.
us?
Yeah.
Okay. Yeah.
Yeah. Can I make a comment? I agree with Barbara that we don't know where these will fit in. I kind of have the feeling now when it comes to quantum coding that, since there are no qubits out there that are below threshold for any codes, essentially at the moment, we should be investigating everything when it comes to quantum codes, and who knows what will prove useful, and perhaps certain codes will prove more useful for certain platforms. I mean, some platforms may be constrained more for geometric locality. Maybe these codes won't be useful for those platforms. Maybe these codes will be useful though for communicating between, different devices. Maybe they'll have something built on a two-dimensional surface and they'll be constrained to that code, but maybe they'll communicate with some other quantum device and these codes will be useful. So I think practically, we need to investigate everything. It's familiar from standard classical error correction that use different codes for different communication channels. So I think right now, until we have an actual physical device, we should be doing everything.
Yeah, I think that's a very good point. I was actually wondering whether you have, you've also worked on Floquet codes, Matt, and whether you have, would there be a quantum LDPC version of a Floquet code? Because that sounds like
I don't know. It's a good question. And I've been trying to wonder if can these Floquet codes be interpreted in some more standard homological formulation, which makes it clear? I don't know. It's definitely an interesting open question to try to investigate that. I just want to add something else. I don't want to derail too much. There's the practical interest, but then I think these are really fascinating mathematically for a lot of reasons. It's a fundamental thing in coding theory. It's a fundamental thing in quantum complexity theory. It may let you prove things that might lead to a quantum PCP theorem. And, I'll just, if I can advertise a piece of my own work with Mike Friedman and I, we had a lot of the early codes, like the Kitaev code, the toric code, and then Friedman-Meyer-Luo came from starting with something in topology, some manifold in topology, like a torus, or Friedman-Meyer-Luo was a much more complicated manifold, as Anthony said, and then building a code from that. So Mike Friedman and I kind of came up with a construction to take one of these codes and turn it back into a manifold so that the toric code on that manifold has these large distance properties and so on. Not a two-dimensional manifold, a much higher dimensional manifold. And it leads to some interesting constructions in geometry. So I think from the point of view of math, these codes are just incredibly interesting too.
Sorry, so can you say a little bit more about what this what this potential path towards quantum PCP might look like? If what does this open up in terms of in terms of getting there?
Well, I mean, we would want, I guess, the nicest first thing would be to get like this NLTS conjecture, which is that there's some Hamiltonian where no low energy state is related to the product state by a circuit. That's a requirement for quantum PCP, and you might hope that these codes, something like these codes, might have these properties. I guess in one sense, like they lead to classical locally testable codes, and maybe some version of them could lead to a quantum locally testable code. It just seems like the next big breakthrough in coding theory. 3 years ago, like I could not dream that someone would write down a linear distance code, and now this is done. Like the two big breakthroughs clearly are now making it efficiently decodable, and I think making a locally testable quantum code. I don't know how to do it. If I knew how to do it, maybe. But it just seems so exciting that, like, how can this be? How can they have written down such a good code?
Yeah.
So I certainly want to second everything that Matt and Barbara have said. I mean, I agree that finding kind of practical protocols using these LDPC codes is a pretty important open problem still. Let me add another one that I think is not really on people's radars that I think might also follow from this result, which is another longstanding open question of the quantum channel capacity, even the quantum channel capacity of the depolarizing channel. So that's a very simple channel, and yet we know that you can do slightly better, very slightly better, for the channel capacity of the depolarizing channel than you could with a random code. And the reason for that is that you can have codes where errors collide, where they do the same thing. And so they kind of fill up less space in the Hilbert space, and you can fit more code words in. And we only know how to do this by a very, very little bit. But maybe it's possible to do a lot better, because the upper bounds are nowhere near what we can do right now. And the way to do that would be to have codes where there's a lot of errors colliding. And what that means is that the code would be an LDPC code. It doesn't necessarily have to be a good LDPC code, because of the difference between typical errors and worst case error. But that's a good place to look, right? And so maybe similar types of constructions or somehow other inspired by this result would let us find codes that actually can kind of push the quantum channel capacity, maybe even well beyond what we can do right now, and maybe even help us understand actually what the actual upper limit is to superadditivity of channel capacity. That would be great.
So if you were interested only in random errors, is there a much better, much simpler construction of quantum LDPC codes?
I mean, so the square root of n hypergraph product codes, that's already good enough for correcting typical errors. It's possible, and again, we don't have all the decoders worked out, but it's possible that these linear distance codes could do better in terms of threshold, but it's possible they're not, right? So this is again another class of questions that still need to be answered.
Yeah.
Can I make a comment too? Partly because I feel like there's like way too much agreement on this panel, and always we should have a little disagreement on the panel. But I want to, Barbara and Daniel are both saying threshold is important, and that's definitely incredibly important. But I just want to like emphasize one of the reasons I think that distance is also very important, which is that if you're significantly below threshold, which is where you would like to operate, because you wouldn't want to operate near threshold, because then your code sizes will be enormous, and you're interested in very low logical error rates, you might really be worrying about errors that are occurring close to the minimum distance. You might be wanting to operate your code in the regime where the most likely error is a minimum distance error rather than a typical error. So I think this is something I'm kind of coming around to more, and that maybe this linear distance really is an advantage. At first you think, oh, this is rare errors, but we might, if we want to get logical error rates of 10 to the minus 15 or something, we need to be dealing with that, and we don't want to be close to threshold.
That's true, but in the spirit of disagreement, You kind of need both. I mean, so if you can keep the threshold and improve the minimum distance, I think that's true. But if it's a matter of trading off threshold versus minimum distance, well, you still have to be some distance below the threshold, right? And so if the threshold is higher for the same physical error rate, you're going to be further below the threshold if the threshold is higher. So, I mean, obviously, you have to look at kind of all the spectrum codes you have available and put everything together and all your fault-tolerant protocols to see what's actually the best thing to do. But I agree that there will be some regimes where a linear distance code is better, but there, depending on what code's available, there are also regimes where it's not.
Yeah, I mean, I agree. Like for a lot of codes, like a heuristic for the logical error rate, which works kind of reasonably well, is the logical error rate is physical error rate divided by threshold raised to the distance on 2. I mean, you should correct it a little bit, but that's kind of like your first back of the envelope. So yeah, they clearly both matter.
Yeah, and I think I stressed threshold because that is a current bottleneck in terms of experimental progress, because it's just incredibly hard to get error rates of 10⁻³ or something. It's in a scalable manner, right? Everybody knows this, otherwise our field would have progressed much faster. I mean, so it's just focusing on the most relevant bottleneck. It's not, yeah. But another point I wanted to make is maybe this is actually a question to Anthony. So I think it's also interesting to have concrete constructive constructions, right? So not just randomized constructions of the existence of code families. Can you comment on that? Because I know there's some constructions, but not all of them are explicit constructions that you could, test for a threshold or do other numerics on. And also small constructions would be interesting.
Yeah, so for the new codes, for the Proton-Taylor codes, I mean, it's very easy to look at explicit examples. So you just need to you need a group with 2 subsets. So any group will do. And you need a small code. So I mean, if you want the asymptotic results, you want to take large small codes, which will behave like typical random codes. But if you want small examples, you could take, classical codes of length 7 and, like BCH code like this that have distance 3 and are dual. So you need both the code and its dual to have large distance. But you can do that with, small codes of length 7. And then, so then it means that you take any group that you want. So it's fairly easy to get small examples with like about 400 qubits. You can have a dimension that is not too bad, but a few tens. But for this size of codes, the scaling of the distance, it won't show up. You still get small distances. So the kind of the point where the regime where you start beating, the square root n distance, probably you have to go higher with this construction. You probably need a few thousands of qubits, 10,000 qubits, I don't know. So it's easy to devise small examples, a few hundred qubits. This won't have like a great distance, not too bad, but not great. If you want better distance, you need longer codes or better constructions.
Yeah, so I guess I don't have a good overview of all the constructions, but I think that is also sort of maybe a challenge to that you would like to have good small constructions for if you want to study some properties that may be relevant practically, right?
Yeah, of course. Yeah.
So
this we don't have now.
I had a sort of naive question for you, Daniel. In the fault tolerance construction with quantum LDPC codes. So, what is the level of parallelism that you can achieve in applying gates? So now you have n qubits or some constant times n qubits encoded in this code, and what are you doing under the covers with it?
So there's a trade-off. You need sublinear parallelism. So there's so the way my construction works, which probably is not the only way or the best way to do it, but it's just a way that is easy to prove, is instead of using one giant code to encode your whole computation, is to use smaller blocks of sublinear size. And the reason for that is that when you want to do gates, you need kind of additional ancillas that are the size of a block. Actually, they are a block with, ancilla qubit, logical ancilla qubits. So there's a trade-off then, because if you want to do gates, you have to, the size of the block times the amount of parallelism you have, that's kind of the number of ancillas that you need. And so if you want more parallelism, you can decrease the size of the block further, and then you can have more logical gates in parallel. But the problem is that when you decrease the size of the block, you'll get slower scaling of everything else and protecting against errors. So you probably have to push up to bigger and bigger sizes before it actually becomes, makes it work, right? There's some like threshold value threshold size where you can say, well, the overhead is less than this amount. But in principle, you can do that for any sublinear amount of parallelism. Now, again, there may be some totally different approach that doesn't have this problem and lets you do linear parallelism. That's another open question that's very interesting. Mm-hmm. So I had a question or a comment.
I actually have several questions, but let me start with one. I'm curious if there might be thinking out of the box. In many ways, these LDPC codes, which I'm very excited by, are not very exciting to the experimentalists because they're very worried about the high connectivity that may be required between qubits in these systems. So more realistically, to many of my colleagues doing experiment are specialized error correction codes, which are much more quantum in many ways. Bosonic error correction codes which deal with just erasure, for example. So are there going to be, does this inspire you to think of truly quantum codes that have really very little connection with classical error correction and codes which dominantly handle one kind of error, like quantum erasure error or amplitude damping?
So first of all, I don't think you can ever get away from codes that are totally different than classical codes. I mean, even like GKP codes for bosonic things, those have a classical analog, which is just discretizing things. I'm always a little kind of wary of codes that kind of predominantly only treat one kind of error, because in a real system, there's many kinds of errors, and maybe one of them is bigger, and so it's worth having codes that are better at treating one kind of error. But once you knock it down even just a little bit, you'll start to get other kinds of errors, I think, and you're really going to have to deal with a broad spectrum. And moreover, the process of making it fault tolerant, we just don't know how to deal with most kinds of errors. There's specific kinds like dephasing. There's been a lot of progress on dealing with dephasing errors fault tolerantly. Erasure errors happen to be pretty easy to deal with fault tolerantly. They require like the same thing. But almost anything else like amplitude damping, I have no idea how to do that fault tolerantly without just correcting everything. That's something that we might see progress in soon, who knows? But I think the important thing to remember is that this is like a really hard problem in general, dealing with the fault tolerance and dealing with errors. And we're kind of just going to be throwing everything we have at it for the next couple of decades, maybe. And so, if you talk about bosonic codes, typically people are not thinking that the bosonic code is just all they have to do, right? They're going to concatenate that bosonic code with some other code, or maybe some other kind of hybrid code like that. So, there's a lot of tricks. And just to get back to your very first point about the connectivity, that's obviously a really important question. these high rate LDPC codes cannot be embedded in finite dimensions. But there are some implementations where that's not such a big constraint, like photonic ones, or even ion traps where you have smaller traps connected by long range things. And moreover, I mean, it's logically possible that we can somehow fit these LDPC codes into 2 dimensions with only kind of a limited amount of long range connectivity and get around that and still be able to do error correction and fault tolerance. That's like pure speculation, but I have a student looking at that, and it might be possible.
So that would be C5 codes with low connectivity or something.
I mean, who knows, right? It's too early to really say, but yeah. So so I don't think the low connectivity is necessarily a deal. I mean, the high connectivity needed is necessarily a deal breaker, but obviously it's a drawback of these codes versus surface code, and that will continue to be true, presumably, even if we come up with otherwise practical protocols.
Another question is, I have no good ideas about this, but besides connectivity, it's the other parameters of the codes are, what's the parity check weight and what's the degree? So how many parity checks does every qubit participate in? And as far as I can tell, there are no sort of no-go results there that say, I mean, there are some no-go results of very low, parity check weight 2 and so on. You can't make a code, but it's not like, you can say, well, how far can we minimize these weights? And I know people have tried to do that in some constructions, but yeah, so I wonder also about optimizing that. What are the possibilities there, or showing that it's not possible? Because that's another experimental constraint, of course.
Yeah, any LDPC code could be made. I forget exactly what the number is, but the parity check weights and stuff can somewhere, it's like around 5 to 8 or something. You can make them all like not some ridiculously big number, even if they start as some really big number. If it starts off one, it can get to some.
You can make them weight 5, you're saying, or
something
8?
Like that. I forget the exact number, somewhere in that range.
And then you just the distance and the
Those go
are still
back by
linear.
constant factors.
Yeah, there's some constant loss.
No, the constant factor loss depends upon what they were initially. So if initially they were, 1 million, when you get down to 5, you only lose a constant factor in the distance.
Right. Yeah. So okay, you're okay then. Yeah. But then the other degree is also included.
Yeah,
there?
yeah, they can be some number around there. I forget the exact number.
Yeah. Yeah, thanks.
I want to poke another hole if there's time for me to ask one more. How about non-stabilizer codes? I still really love these new dimensions that are coming out, like that started with, CWS codes were one of them, but it seems to have grown. Do you have optimism about that direction? Anyone on the panel?
Well, for what purpose, right? I think, for mathematical studies or interest, I think anything goes I think it's fascinating, but yeah.
Or specifically, I don't know a single fault-tolerant construction for those, and I've always been curious to even come up with one, because maybe then it would be something that's uniquely quantum and not terribly classical.
I of course have a conflict of interest with having optimism about non-stabilizer codes, but the one family I think that has some clear value fault tolerantly is non-abelian anyons, which don't have any stabilizer realization, but clearly provide some degree of fault tolerance, although not necessarily everything you want.
And the motivation there would be these kinds of codes might lead to Hamiltonians, which then give you a sense of some natural stability, like you say.
Yeah, although, they don't actually, right? Just like this, the Tor code doesn't actually provide self-correction. But, maybe there's some higher dimensional, four-dimensional non-abelian things with strings and walls and stuff like that does do that.
Or at least in the CWS code, you need only use one classical code for the construction. And then it has to correct these other strange patterns of errors because of this XZ duality, that an X error turns into a higher weight Z error, for example. And then maybe there could be new LDPC constructions made from sophisticated classical codes that correct multiple errors.
I mean, honestly, I'm not completely sure how you would define a non-stabilizer LDPC code. I mean, you can come up with definitions, but there's not like an obviously correct one.
Any other questions from the audience? In the meantime, let me ask Anthony. You may have touched on this already, but was there a sense of, was it just a big coincidence that that classical, locally testable codes sort of coincided with this quantum LDPC code? So is it? Was that a coincidence, or is there something more basic going on there?
It's a very good question. Probably you would have to ask, the authors of the two papers. Yeah, I mean, the fact that these quantum LDPC codes with good distance, they give you, so it's not necessarily true always, but for all the constructions that we know, they give you, classical locally testable codes. Yeah, it's a bit surprising. I don't know if people, I don't know Poulin and KLHF noticed that, because in Insight, you can see that somehow the LTCs, they are hidden somewhere, but you have to look for them. Yeah, I don't know. I don't know. I mean, in our case, so for the codes that we have, so it's kind of, so we were with Gilles Zemmour, we were looking at we are trying to find a decoder for the code of Poulin and KLHF, and while we are trying to do that, somehow we found ways to simplify the codes, and little by little we came closer and closer to the Dinier et al. Construction, and at the end we realized, okay, the Dinier et al. Construction is hidden just here. So so we went from the Russian code to the Israeli code because we are looking for a decoder. And in Insight, maybe it's kind of obvious that these two things are related, but it's not clear to me. Even when you know that they are connected, I mean, at some point I knew how to prove. I mean, it was the local testability. It's just a corollary of our result. But then, so we wrote the proof, and then a couple of weeks later, I wanted to remember, and I couldn't remember how it goes. So it's there, but it's not so trivial. The connection is not so easy to spot. So I don't know how KLHF and Poulin they caught this connection when they wrote the paper. I don't know. But it's very intriguing that there is this connection.
Yeah, extremely. So any other comments from the panel, or any other questions?
There's a question in the Q&A.
Oh, okay. Okay, so the question says, any comments on the potential impact that emerging fields such as homotopy theory, type theory could have in the future of quantum computation? I don't know if somebody wants to. Daniel, did you want to address that? Or?
No, I have no idea. I was hoping Matt or Anthony would, or Barbara or anybody else would have an answer on that.
No answer.
Okay. Okay. So, anything else that Anyone on the panel wants to say? Any last thoughts? Otherwise, again, let's thank Anthony for a fantastic talk and panel for really great discussion. And we'll see you next week. Okay, thank you, Anthony, Daniel, Barbara, and Matt.
Thanks.